Yes. Hello. Yes, I'm here in front of many free places, so everybody's at the Jahresrückblick. So, and you are the persons who really are interested in this topic. I hope, or you are the last who cannot get inside because it's full. Okay. Oh, this way. Whatever. I want to talk about privacy-enhanced event scheduling today. And before I start with a real insight, what I mean is I want first to define what privacy-enhanced event scheduling means. So event scheduling itself, maybe some of you know from several applications. So some of you may know this Thunderbird, or we have here something which is from Evolution, which is quite similar to the Outlook client where you can schedule some events. This one is probably well known. It's the Doodle application, which became very popular in last times. And here we have a new application from the German Post named Zeitfinder. And all these applications have something in common. You give them your availability pattern, which is the pattern when you are available at certain timestamps, and then you can calculate the day or the time slot where everybody can participate in some event, and then with this thing you can schedule some event. So these solutions all share two privacy problems. So the first one is the direct inference. This is what you can directly read out of such an availability pattern. So for example, we have here the availability pattern of John, and John's wife may ask, yes, so will my husband just vote for the date on our wedding anniversary? And you can directly go into this doodle poll and look, okay, here's the business dinner, and he prefers to go to the business dinner instead of doing something with me. Okay, so the next thing is the indirect inference. This is what happens, if we connect two or more sources where we can get information. For example, here we have two calendars. One is taken from the Sunbird, and one other is a doodle poll, which polls about some chat. And maybe the boss of John can ask herself, hey, this availability pattern of the user Bunny23 looks quite similar to the availability pattern of my employee John Doe. So, and with this you can, at the first thing, get some information about this pseudonym, and then get information about other availability patterns he do not have in his calendar and these things. And when we talked about these things at the meal at a colleague of mine, so we were sitting there and his wife was sitting at the table with us, and we talked about this, and she said, yes, every time my boss is unavailable, I'm looking into our calendar and I'm looking who has an appointment of the same size my boss has, and from there she can infer who is in the meeting with her boss. So, and this is directly, this is the indirect inference you have with these polls. So, after defining the thing, so what we want to have, this privacy-enhanced solution for this problem, I will go a bit more in this problem statement, what it's distinguished from e-voting, because from the first thing it looks a bit like some e-voting solution we already have. Tell you the scheme afterwards, some extensions, and evaluate it, and hopefully come to some demo afterwards of a first implementation of it. So if you have questions, I will stop at these topics every time, and if you have questions, so please don't hesitate to ask. I think we have enough time to answer them directly so that you do not have some understanding problems. Okay, so at first we have some requirements. And the first requirement we have always is we have an untrusted server, because with a trusted server we can solve all the problems. He takes all the dates, all the time slots, and afterwards says what is the best time slot. From this untrusted server, with no trusted entity, there come other problems. Two contradicting requirements, which are, at the one side, we want to have a privacy-friendly solution so that nobody can see what we have voted for. But on the other side, the contradicting thing is we want to have the verifiability, so you want to see what the others have voted, or at least want to have a proof that they haven't cheated the protocol. So this is something which already occurs in e-voting solutions, and we will talk about this later. So, and the last two things are, at the one side we want to have few messages, which makes the whole protocol more usable. So think of a protocol which needs about 10 times you have to sign first a message, so then wait 1 hour after everybody signed something, then you have to send a message back, and you have to do this and this. So this would lead to an unusable implementation. And of course we want to have a low computational complexity. So I talked a lot about the thing that it's quite similar to e-voting, but it also distinguishes from e-voting. I will show you what is the difference. So in e-voting, we typically have solutions which look like this. So we have a voting ballot where we have many candidates, and you can make one cross at one candidate there. So sometimes you have 3 votes, so then you make the e-voting scheme 3 times, all these things, but they are optimized to scale in this dimension so that you have many candidates. In the event scheduling thing, it's a bit different because you have really many time slots. So think of an extreme example where you have want to have a telephone conference in the next 2 weeks, and we schedule the meeting quarterly. So you have an 8-hour working day times 4 makes times 2 weeks makes 320 time slots, and everybody wants to give his really fine-grained availability pattern to this to calculate the optimal date or the optimal time slot. And therefore, this has to scale in this dimension. So it does not apply directly that we can make several instantiations of the e-voting scenario. And one other thing applies to the e-voting thing, because if you think of an e-voting scheme, it typically has to be applied to 80 million Germans or to millions of inhabitants in the United States or anywhere. So therefore, it has to scale in this dimension too, which is a difference to the event scheduling to other thing, because we only have small groups of 5 to 10 people, and these want to schedule something, or maybe we have then some other applications in mind, maybe so to vote for what is the cinema film we want to visit, or these things. So after this explanation, after this start, I want to explain you the scheme. So don't worry, it's not so complicated as shown here, and I will only explain you this part. So I will try to make it really understandable. And for the first thing, I want to recall to cryptographic primitives. So first one and afterwards one other, which is the main idea of the whole protocol. So the primitive I'm talking about is superposed sending, also known as the DC network, which was introduced by David Chaum as the dining cryptographs problem. So this is a protocol for sending a message anonymously. So think of three people, Alice, Bob, and Carol, who wants to send a message and want to be anonymous while sending this message. So the first thing what they do is everybody exchanges a key, which is just a random number. And when we look into one such key exchange, Alice and Bob store the pairwise inverse number of this key. I excluded the modulo things here to make it a bit easier to read, and skipped some math inside, but the thing is that we calculate in some group and they store the pairwise inverse number. So afterwards, after every participant exchanged some key, we have on this slide once the KAB in the positive form and once minus KAB, plus KBC and minus, and here is minus KAC and plus KAC. So every number is on this slide, once in the positive form and once in the negative form. So when we now want to send the message, everybody takes this message and adds the key to the message or subtracts it in the way. So when now sending this message to some single server or distributing it under the participants, you cannot infer on this way if there is some message inside or which message is inside, because this message is encrypted with these two numbers in a